Hey guys, in this video I am going to review the questions where less than 50% of you got it correct from the most recent test. So please follow along using your test and make sure that you go through these concepts. The first one is going to be number 4. In this question, you are given the graph of the derivative as shown above. The line tangent to the derivative at x equals 0 is vertical, and f prime is not differentiable at x equals 2. Which of the following statements is true? F prime does not exist at x equals 2. Well, that's not true because f prime at x equals 2 is a point. It exists. It's right there. F is decreasing on the interval from 2 to 4. If f is decreasing on an interval, then f prime is less than 0 on that interval. So let's take a look at from 2 to 4. From 2 to 4, f prime, which is these y values right here, because this is the graph of f prime, those are positive. So f prime is not decreasing on that interval. The graph of f has a point of inflection at x equals 2. Points of inflection occur where the second derivative is equal to 0 or where the second derivative is undefined and there's a sign change. Okay, so we have two possible points of inflection here. Here we have a vertical tangent. So we have, this is a vertical tangent, so the derivative of this function, the second derivative, which is the derivative of the first derivative, the second derivative is undefined here, and the second derivative is undefined here. So we have two possible points of inflection, one at 0 and one at 2. And this is, we're talking about the second derivative here. I'll say that one more time. The second derivative is undefined at x equals 0 and at x equals 2. And I know that because, I should have written 2 there, 2. We know that because there's a vertical tangent here. And we know that because of the cusp there. And there are no places where the second derivative is 0 because there are no horizontal tangents here. We are looking at the first derivative. So let's check our signs. Our slopes are positive before 0 and positive after 0. Let me use a different color there, positive, positive. And then before 2, our slopes are positive, and then after 2, our slopes are negative. So it looks like 2 is where the point of inflection is. So right now, D is also out. F has a local maximum at x equals 0. At x equals 0, we do have f prime of x does equal 0 at x equals 0. And if you take a look at the signs of f prime, we have a negative and positive. So it does not have a local max. It actually has a local min at x equals 0 because we're going from decreasing to increasing if we're looking at the signs of f prime, which are negative and positive on the both sides of 0. So the answer is C. The next question where less than 50% of you got it correct is question 7. This was a calculator allowed question, so this question should have been quite simple. It says the first derivative of the function is given by f prime of x equals sine x squared. At which of the following values does f have a local minimum? So since you have a calculator, you want to graph the derivative, and you want to look for zeros. You want to look for zeros where the sign changes from, since it's a local minimum, from negative to positive. So for example, let's say you've got something like this. Here's a 0, and here's a sign change from negative to positive because you are graphing the derivative itself. And those would be locations where f has a local minimum. And you have to be able to pull that 0 from your calculator. So this was 100% calculator use. The next one where 40-something% of you got it wrong was number 8. If the limit as x approaches a of f of x equals f of a, then which of the following statements must be true? The first one says f is continuous at x equals a. This is the definition of continuity. The limit as x approaches a of x is f of a. So, I mean, that's pretty much the definition, but let's keep looking. F is differentiable at x equals a. Not necessarily true. You can be continuous and not differentiable, so that's out. For all values of x, f of x equals f of a. That doesn't even make sense. No. The line y equals f of a is tangent to the graph of f at x equals a. This has nothing to do with the derivative. This is just saying that the limit from the left and the limit from the right is equal to the function values. So this says nothing about the derivative, so no. And there's nothing about a vertical asymptote either. So this one should have been pretty simple. This was simply the definition of continuity, which is that the limit exists. So the limit from the left and the right exists, and it is equal to f of a. All right, on number 19 here, we're looking for what value of x does it have a point of does the function have a point of inflection? So we are going to take the derivative. We are deriving y equals x to the negative 2 minus x to the negative third. So the first derivative is negative 2x to the negative 3 plus, all right, where was I here? Okay, plus 3x to the negative 4. And then we need the second derivative here because we are looking for points of inflection. So let's go one more time. We have 6x to the negative 4 minus 12x to the negative 5. All right, so the second derivative is 6 over x to the 4th minus 12 over x to the 5th. If we add that up and set it equal to 0, let me go ahead and do that. That is going to be 6x minus 12 over x to the 5th, and that's equal to the second derivative. And I did that by multiplying by x there to make common denominators. Now we're going to want to set that equal to 0. So, and we're going to want to look where it's undefined. So y double prime is equal to 0 when x is equal to 2. And y double prime is undefined when x is equal to 0. Whoops, 0. Okay, so 0 makes it undefined, 2 makes it 0. So we have two possible points of inflection, one at 0 and one at 2. We need to check for sign changes for points of inflection. So this is our second derivative. Let's check sign changes here. If I plug in a negative, let's say negative 1, we've got negative 6 minus 12, which is negative, over negative to the 5th power, which is also negative, so that's going to be positive. If I plug in 1, let's say, I've got 6 minus 12, which will be negative, over a positive, so that will be negative. And if I plug in, let's say, 3, I'll have a positive over a positive, so that will be positive. Uh-oh. You heard that uh-oh, right? Uh-oh, big uh-oh. What do we do? There's 2 points of inflection, and I can only pick one answer. I can either say 0 or I can say 2. So this is where you go think, 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 think. You have a vertical asymptote at x equals 0. You cannot have a point of inflection at a vertical asymptote. Yes, there will be a vertical asymptote, maybe it's concave up and then it's going to be concave down on either side of the asymptote, but that doesn't mean that it's a point of inflection. It's just that the asymptote is showing a change of inflection. So this, even though it was a candidate for a point of inflection, it can't be a candidate for a point of inflection because originally we have a vertical asymptote there. So the only candidate is C, x equals 2. So those are those uh-oh moments. You're like, wait, let me go back, let me think, let me look at my function and look at that function and say, wait a minute. Okay, I do have a situation here where I have vertical asymptotes. We can't have points of inflection on asymptotes. Okay, the next one was number 24. If y equals sine x cosine x, then x at equals pi over 3 is what? Oh, then at x equals pi over 3, what's dy dx? So we're just taking the derivative of sine x cosine x and then evaluating it at pi over 3. So y prime, we've got a product rule. So the first times derivative of the second, which is negative sine x, so let's put that negative in the front, plus the second times derivative of the first. So we're doing negative sine squared x plus cosine squared x. Okay, so we're doing negative sine squared at pi over 3 plus cosine squared at pi over 3. And that is y prime equals y prime at pi over 3 equals. Okay, so what's pi over 3? Pi over 3 is 60. I'm going to do real quick my 1, 2, 3, 3, 2, 1. Sine, cosine. Here's 60 because it's 30, 45, 60. So sine at pi over 3 is square root of 3 over 2. And we're going to square that to make 3 over 4, and it's going to be negative. Okay, so sine again, sine at pi over 3, or sine of pi over 3 equals square root of 3 over 2. If you square that, you're going to get 3/4, and then place the negative on it. Cosine at pi over 3 is 1/2. Square that, that's 1/4. All right, guys? And then you'll get your answer of, where is it? A. All right, the next one is number 27. And I just cut and pasted it here. There's no reason why E is bigger. It's just because it didn't fit on the screen. So it says, here's the graph of the function shown above. Which of the following could be the graph of the derivative? And E's whatever on the bottom. Okay, so this is the graph of the function. The function is decreasing from, let's call that around, what, 2. So, ish. So decreasing and then increasing. So what this is telling me is that f prime should be negative, and this is telling me that f prime should be positive. I also have a horizontal tangent at this 2, so at f prime of, let's call it 2, that's equal to 0. All right. I'm concave down from 0 to 2, so f double prime is less than 0 from 0 to 2. And I'm concave down from 0 to 2. No, not 0 to 2, I'm sorry. Sorry. Concave down from 0 to like somewhere over here where I start to change to concave up, because you've got upwards concavity right in this little pocket right here. So let's say like to about 1. If we call that 1, and let's call that 3. So we're concave down from 0 to 1 and concave down from 3 to 4. So from 0 to 1 and from 3 to 4, which means that's the slope of the tangent on the derivative. And it looks like we are concave up from that 1 to 3. And we're just going to call those numbers what they are. Okay? And then, so we need to find a function that does that. So let's look for one that has a 0 at x equals 2, because we're looking for the graph of the derivative. So if we narrow it down, finding that 2, I don't have a 0 there. I do have a 0 here. I do have a 0 here. I do have a 0 here. So that narrows us down to B, and I don't have a 0 on E. So E's out and A is out. Okay? Now, our first derivative, because our function is decreasing from 0 to 2 and then increasing from 2 to 4. So our first derivative has to be negative here and then positive here. So negative, positive, okay, that's an option. Negative, positive, okay, that's an option. Positive, positive, okay, that's not. Out. Goodbye. All right, now the decision is between C and D, and it's going to boil down to that concavity, and this could be what got you guys here. So we are changing concavity at 1 and at 3, okay? So our second derivative, which means our slopes should be negative from 0 to 1. Their slopes are positive the entire time. So this is telling me concave up all the time, because this is the first derivative, and the derivative of the derivative is positive the entire time. So already that one's out. But let's check it here. So you're concave down, you're negative, 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 then positive, positive, positive. See? There's a POI. POI. Boom. POI. Which is exactly where we wanted them to be, at 1 and at 3, as we called them. So POI, POI, that matches the criteria. The answer is D. All right, guys, this next one is number 28. The majority of you put D, but the answer is actually C. And I can understand why you would get confused and think that D was the correct answer, but let's go ahead and take a look at this. So the first one is saying that the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right. Nobody chose anything with 1 in it, so you all knew that that was not correct, okay? Because the limit as x approaches 1 from the left is 1, and that's not equal to 0, which is the limit as x approaches 1 from the right, okay? Now, if we take the derivative of this piecewise, and we take it correctly, which the majority of you did, you've got 3 for the first piece for x is less than 1, and you've got 3 over 3x minus 2 for 1 over u du for x is greater than or equal to 1. Okay? Now these two things are asking two different questions. I can tell you right now, without checking number 2, that number 3 is not true. Number 3 is not true. Without checking number 2, number 3 is not true. Why? Because number 1 needed to be true in order for it to be possibly be differentiable. Number 1 is talking about continuity. If the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right, and that's equal to f of 1, which f of 1 is 0, then the function would be continuous. So since number 1 is not true, the function is not continuous. Automatically, if you are not continuous, you are not differentiable. So number 1 was false. The function was not continuous at 1, therefore it is not differentiable at 1. So already, anything with 3 is out. Anything with 1 is out. Okay? So I'll say that one more time. 1 was out because the limits were not equal on the left and on the right. As a result, the function is not continuous at 1, therefore it's automatically not differentiable at 1. Differentiability implies continuity, but the contrapositive, I believe, is the way you say it. If it's not continuous, it's automatically not differentiable at 1. That's different than what question 2 is asking you. Question 2 is asking you, on the derivative, as you're approaching 1 from the left and 1 from the right, what is y approaching? Y may not equal something, but it could be approaching something. So let's check that. Here's the derivative. As we approach 1 from the left, we get 3. As we approach 1 from the right, we also get 3. So the limit as x approaches 1 from the left and the right of the derivative, the limits are equal from the left and the right. So 2 is the only thing that is true. 2 has nothing to do with differentiability or continuity because all 2 is asking you is on the graph of the derivative as we're coming at 1 from the left and from the right, what does y approach? I know you cannot use calculators on this question, but I just want to show you the graphs so that you can kind of get a visual. So let's take a look at those real quick. All right, so right here we've got a graph of the function that's showing the discontinuity at 1. Here we've got a graph of the derivative. Now the derivative does have a corner here. That just means that the derivative itself is not differentiable at 1. But that is not relevant because you know, it's not even defined here. It's not defined here because it's not continuous there. Now you can't see that on this particular graphing calculator. But the derivative is not defined here because it's not continuous there to begin with. Okay? So the first question, like I said, was false. The limit to the left and to the right does not match. As a result, the function is not differentiable at 1. But on the graph of the derivative, which is over here, as it's approaching 1 from the left and approaching 1 from the right, y is approaching the same value, even though it can't equal this value because we are not differentiable at 1. It can't equal 3, but it is approaching 3. And that's the difference between the two questions. This question is asking you about differentiability, where this question is just asking you about the limit. If you're looking at a function, in this case the derivative, if one is coming from the left and one is coming from the right, are they the same? Are those values the same? Yes, they are. We're not asking, number 2 is not asking about differentiability. So I hope that clears that one up. That was, again, number 28. Okay, this one is a little bit tricky, but we're going to go ahead and start by, this is number, I forget what number this is. This is number 32. All right, we're going to start by taking the derivative because we're looking for values of k. K is a constant. We're looking for what values of k is f strictly decreasing on the interval from -1 to 1. All right, so first thing we're going to do is we're going to take the derivative. So it's imperative that you derive appropriately here, all over x squared plus 1 squared. All right, and then we're going to set that derivative equal to 0 and look for critical values, because that might help me kind of think about this a little bit. There are no places where the derivative is undefined, so I don't have to worry about those critical values, because if you take a look at this, this will always be positive. So this is always positive. All right. So we're going to go ahead and set kx squared plus k minus 2kx squared, which is my numerator, equal to 0. I could take out a k. If I take out a k and simplify, I end up with negative x squared plus 1 is equal to 0. Take out a k again, and this is a difference of squares, so I get 1 minus x, 1 plus x equals 0. So it looks like I have critical values at x equals 1 and at x equals negative 1. All right, so we do have a critical value at negative 1 and at 1. So it looks like if we take this and just rewrite it as 1 minus x over 1 plus x all over x squared, because this is the, that's the numerator simplified. We did it over here. Over x squared plus 1 squared, and we're keeping in mind that that denominator is always positive. Let's just take a look at increasing and decreasing without thinking about k. All right, because we kind of have k isolated out here. Let's think about increasing and decreasing without thinking about k. So if we plug in negative 2 into the derivative, this is always positive, so negative 2 will make this 1 minus minus 2, so that'll be positive. 1 plus negative 2, that will be negative, so this is going to be negative. Again, we're doing this without thinking about k, so we're kind of going to put a box on k for a second. Let's plug in 0, 0, 0, positive, positive, positive. And we are looking at the interval between negative 1 and 1, so we're going to look right in here for a second. But I'm going to just keep going just to prove a point here. So 2 will make everything positive. Okay, so the question is for what values of, now let's move this little guy. No, it's not going to let me move the box. Okay, I'll just put k right there. For what values of k will this interval be strictly decreasing? Right now this interval is strictly increasing. So if k is negative, if k is less than 0, will this interval change to decreasing? Yeah, because let's say we plug in 0, which is in between negative 1 and 1. If we plug in 0, that's positive, that's positive, that's positive. If this guy's negative, he's going to make the whole thing negative. Okay, let's check the other ones just for fun. What if k is 0? Well, if k is 0, then it becomes 0 times, let's again plug in 0. 0 times 1 times 1, so it's just going to be 0, so that's not going to work. What if k is positive? Well, it's going to be a positive times a positive times a positive over a positive, because we're using the interval between negative 1 and 1, we're going to go ahead and use 0. What if k is greater than 1? Again, if k is 5, this is a positive times a positive over a positive with a, positive. So the correct answer is if k is less than 0. Number 33, I've given you this same exact question 1,000 times. It is the definition of the derivative. F of x is sine of x, and we are looking for f prime of pi over 3. How do you know that? Because I'm reading the definition of the derivative. So we're looking for the derivative of sine of x at pi over 3. F of x is sine of x. We're looking for f prime of pi over 3. Last one is number 35. We are looking for d theta dt. If you read the question again, we are looking for d theta dt. This is the ladder right here. It is constant. Okay. If we're looking for d theta dt, we want to call a trig function. And we do know dy dt. So let's call a trig function with y in it to make our life much, much easier. Remember that this is the ladder, so this is constant. The ladder is not stretching or shrinking. So we're going to say sine of theta is equal to y over 15. Again, sine of theta is opposite over hypotenuse. Why didn't I put 12 over 15? Because 12 is changing. So I need to derive the formula, and the formula is sine of theta is y over constant. The constant is 15. Now I'm going to take the derivative of this because this is changing. Derivative of sine is cosine theta d theta dt is equal to 1/15 dy dt. Okay, so this was the formula. This was the relationship of this related rates problem. This is changing, this is changing, this is constant. I took the derivative. Now I'm going to plug in what I know. I know cosine theta. At this moment in time, cosine theta is 9 over 15. 9 over 15. Okay, so when we pause the video, and this is 12, and this is 9, and this is 15, we pause the video of the ladder moving down. Cosine at that moment is 9 over 15. I do not know d theta dt, and it's 1/15 times -2. And you can find d theta dt by solving that algebraic equation.